Annomate, an intelligent pen-based assistive technology to improve the phonological and orthographic processing abilities of the dyslexic. The authors are Utkarsh Gautam, Gaurav Srivastav, and Kushagra Singh. Dyslexia is a learning disorder which is mainly characterized by phonological deficit and orthographic processing deficit. The phonological deficit is the inability to associate the correct sound with the correct alphabet. The orthographic processing deficit is the inability to remember the correct structure or look of an alphabet. Statistics show that around 30 million children are known to be dyslexic in India. The fact that dyslexia is such a common problem and that not much work has been done to develop assistive technologies to aid the dyslexic motivated us to develop Annomate. Annomate is the name we have given to our product, which is an autonomous, real-time, and interactive guide that, like a teacher, overlooks the handwriting of a dyslexic and helps them to read and write correctly. Present-day assistive technologies for dyslexic consist of software that focus on improving only the phonological deficit using text-to-speech converters. Other assistive technologies use intelligent pens that scan the writing of the user using optical sensors which are highly expensive. In stark contradiction, Annomate is all-encompassing. That is, it works to improve both the phonological deficit and the orthographic processing deficit. Also, Annomate uses only a single accelerometer to monitor the user's handwriting, making it less expensive and accessible to all. The interactive voice response system of Annomate makes the system user-friendly. In the field of human-computer interaction, there has been substantial development in pen-based input devices and auditory output devices. Jin-Sheng Wang et al. Developed a pen device using triaxial accelerometers and transferred the recorded data using RF module to a personal computer for analysis and handwriting recognition. Sprott R proposed a solution for the grapheme to phoneme conversion, which formed the basis of text-to-speech conversion systems. Our work builds upon the two mentioned technologies of human-computer interaction and seeks to combine the both in order to take inputs from the handwriting of the user and give an auditory response as the output. The basic idea behind Annomate is to analyze the user's handwriting to notify the user of any anomaly in writing or to speak out the alphabet written by the user. Therefore, the Annomate works in two modes, the read mode and the write mode. In the read mode, Annomate analyzes the alphabet that the user has traced with the pen and reads it out using its IVRS, thus helping the association of the correct sound with the correct symbol. In the write mode, Annomate constantly monitors the handwriting of the user, and in case of any anomaly, it notifies the user using IVRS, thereby helping the user remember the correct orthographic look of the alphabet. We have divided our entire project into three submodules, namely the perception submodule to monitor the handwriting of the user, the analysis submodule to analyze the handwriting of the user, and the output submodule to interact with the user using auditory response. Now we will present before you the details of each submodule. This is the block diagram of the perception submodule. It consists of the accelerometer ADXL335, which is a 3-axis accelerometer mounted on a pen. It monitors the motion of the pen and sends its readings to the microcontroller using the microcontroller's 10-bit 8-channel ADC. The microcontroller MA430G2553 is manufactured by Texas Instruments. It is a 16-bit low-power microcontroller. The program for calibration, thresholding, and classification is implemented on the MSP 430 G2553. Calibration is required so that different pen holding styles of the people can be incorporated, while thresholding is done to differentiate the hand tremors from the actual pen motion. In classification, the microcontroller receives the signals from the accelerometer, and after appropriate processing, it classifies them into a horizontal, vertical, or diagonal motion of the pen. A pattern of horizontal, vertical, and diagonal motions is transferred to the analysis submodule. This is the snapshot of the perception submodule. You can see the accelerometer, which can be mounted on top of any pen available with the user, and the microcontroller. This is the block diagram of the analysis submodule. It consists of a handwriting recognition algorithm implemented on MATLAB. We observed that all letters are made of either horizontal, vertical, or diagonal strokes. The algorithm stores the stroke details of each letter and matches the input pattern to the pattern of the strokes of each letter. This way, the rank of each letter is calculated using the formula which you can see on your screen. The letter with the highest rank is selected as the recognized letter. The recognized letter is transmitted to the text-to-speech module. The output submodule consists of the text-to-speech module and the audio conditioning circuit. The audio conditioning circuit consists of three stages: the preamplifier stage, the bandpass filter stage, and the power amplifier stage. The text-to-speech module utilizes two ICs. The TTS-256, which is an 8-bit microprocessor, converts English text supplied to it into allophone codes, which are read by the SpeakJet IC. The SpeakJet IC converts the allophone codes into appropriate sounds of alphabets. These sounds are sent to audio conditioners for a better output. As mentioned before, the audio conditioning circuit consists of three stages: the preamplifier stage, the bandpass filter stage, and the power amplifier stage. The preamplifier stage boosts the sound signals for further conditioning. It utilizes the IC LM386 manufactured by Texas Instruments. The bandpass filter is tuned to operate at audible range of frequencies and filter out other noises. It utilizes the IC NE5532A manufactured by Texas Instruments. The power amplifier stage amplifies the signal power, making it able to drive an 8 ohm speaker. It utilizes the IC LM833, also manufactured by Texas Instruments. Hence, we get the auditory response via the speaker. Here, you can see the results of the handwriting recognition algorithm. In the first image, the input pen motion was one horizontal stroke and one vertical stroke. Therefore, the letter T, having index 20, has the highest rank. The second image shows the robustness of the algorithm. In this case, the input was one horizontal stroke and one vertical stroke, with one additional vertical stroke as noise. Even then, the letter T has the highest rank. This is the result of the output submodule. Via the board plot, you can see that the noise has been filtered and only the audible range of frequency has been extracted. Concluding, this paper proposed the development of an interactive, autonomous, and real-time assistive technology for the aid and rehabilitation of the dyslexic while they write naturally. The applications of our system are infinite. Apart from being an assistive technology, it can be used in providing education and teaching basic speaking and writing skills to children. The limitation our system faces is related with the handwriting recognition algorithm, which can be effectively improved using supervised machine learning. Thank you.